Section 3.9 is about differentials. And this section is really a section to help us be able to estimate something. When we talk about a differential, there's a very specific definition that goes with that, and that definition's down here. dy is equal to f prime of x times dx. So if we're looking for just find the differential, then they're really looking for this type of equation here. But let's talk a little bit more about what we're going to see and how we're going to use this. So think back to that tangent line example. If we look down here, we have this function f of x, and then we could find a tangent line to approximate that. So if we're finding the equation of a tangent line, and I'm sorry I'm scrolling back and forth on this, we said to find the tangent line you have to have a point, and then you have to have a slope. We can find the slope by finding the derivative and then taking the derivative and evaluating it at a specific point. So we're going to call that point x equals c. So then our slope is going to be f prime of x evaluated at a specific x value, which we're going to call c. Our point is going to have an x coordinate, which we're going to call c. And to find the y coordinate, we will plug c into our original function, which we're calling f of x. So to find the equation of that tangent line, everything goes back to that point slope formula. Y minus y1 equals m times x minus x1. But let's substitute in everything we know. So we had a point, we had a slope. If we were to type all of that in, our equation would look something like this. So then if we were to put this in slope-intercept form, solve it for y, we would have the slope, f prime of c, times the group x minus c, plus f of c, which would be our y value associated with that c value. So that's where they're getting this equation from. What would be the tangent line for this function f of x at some generic point c f of c? So what's happening here is that if we are looking at approximating, and we're trying to approximate y values here, and we have this function, here's our function, we could use that tangent line for an approximation as long as our x is really close. So notice our x value here at c would be dead on with what the function at c would be. Those y values are going to be exactly the same because that's that tangent line. But if we move to the right or we move to the left just a little bit, do you see how that y value on that line would be super close to that y value on that function? Same thing here. That y value on this line would be super close to that y value on the function. So as long as we're close enough, and pretend this graph was zoomed in, so as long as we are close enough, and they've just moved over some arbitrary value, and they're calling it delta x. So as long as we are close enough, then that y value on that tangent line would be super close to that y value on that function. Now, if we move over too far, well, let's say we go over here. I'm going to extend this tangent line out. Now, this guy's just not going to be a good fit. Do you see how there's a big gap here? So it's not going to be a good approximation if we move too far out to the left or too far out to the right. But if we're within some kind of reasonable distance from the x value we're curious about, then we could reasonably estimate what's going on with y. So that's really what's going on with differentials. Can we get a reasonable approximation? So going back to that definition, the differential, we're going to use dy to denote the differential. And that formula is just f prime of x times dx. So let's talk about some notation that we're going to see here. So when we see dy, by definition, and this is a definition, by definition, it is f prime of x times dx. This is going to give us an approximate value for y. If we see this notation, the delta y, that means the exact change in y. So one of the first things we're going to do is compare what is the approximate value of y, what is the exact change in y, and how close were they. So you'll see that this is going to be a pretty good estimate. Let's look at a few examples. And the first thing we're going to do is compare a few things. So if we look at number 14, we have this function y equals 6 minus 2x squared. We're looking at x equals negative 2, and our delta x is 0.1. Let's start by finding delta y. Delta y is going to be the exact change in y. So by definition, and this is a definition you may want to write down in your notes, is f of x plus delta x minus f of x. So if we substitute in what we know here, we need to find f of negative 2 plus 0.1. So we're starting at negative 2, and we're going to move to the right 0.1 units. Plug that into the function, and then we're going to subtract f of negative 2. So I'm going to simplify this just a little bit. Negative 2 plus 0.1 is negative 1.9. So we're going to substitute that negative 1.9 in for this x, and then we're going to substitute that negative 2 in for this x. So when I substitute in negative 1.9, I got negative 1.22. And when I substitute in negative 2, I got negative 2. So my final answer is 0.78. So this is the exact. So that's an exact change in that y value. Now let's look for that approximate. So to find the approximate, we need to find dy. dy by definition is f prime of x dx. So now we're using the idea of a differential. So if we were to take the derivative of this function, we would get negative 4x. So then if we substitute in everything we know, that approximate value would be negative 4 times negative 2 times 0.1. And if we were to compute that, we would get 0.8. So this is our approximate change in y. So you can see how close those values are. And that should always happen. It should be reasonably close. So then let's talk about what's going on graphically here. If we were to take this and we were to graph this function, our graph is going to look something like this. And this is not drawn to scale, but you'll get an idea of what's going on. So we wanted to look at what's going around x equals negative 2. So at negative 2, that value is negative 2. So this is down here at negative 2. That's a point that's on the graph. -2, -2. We want to know what's happening when we get really close there. And not only that, but what if we were to move just a hair this way? So we have this tangent line that's going to look like that. It's going to touch that graph at that point. And it's going to be really close at -2. But if we were to move over 0.1 units, then now we're looking at the point to -1.9. So that y value is going to be a little bit different than the y value at -2. So if this were something, where would this be used in real life? Well, what if we were doing with a function that was super complicated here, and we needed to know what was happening if we change x by just a little bit. Instead of being at exactly -2, we need to know what happened to that function if we shift to the right just a hair, 0.1 units. Then this would give us a reasonable estimate for that. So this is all about estimation. The examples we're doing are going to be really nice and easy to deal with, but in real life we know things aren't always nice to deal with. Let's look at another example. Let's look at 15. So we're going to do the same kind of thing there on 15. We want to first figure out the exact change in y. Remember, delta y is the exact. The definition is f of x plus delta x minus f of x. So in this case, our x is -1 and our delta x is 0.01. So -1 plus 0.01 minus f of -1. So I'm going to simplify this. -1 plus 0.01 is -0.99. This is going to give us an exact change in y. So if we plug in a -0.99 into this function, -0.99 gives us 1.9606. I'm going to use 4 decimal places. And if we plug in -1, we're going to get 2. So our change will be -0.0394. Notice that change moved in a negative direction instead of in a positive direction like the other one. So this is the exact change. Now let's look at the approximate change. The approximate change is going to use that differential. So the derivative for this function is 4x cubed. And then if we substitute in everything we know, our x value is -1. Our dx is 0.01. And we're going to get -0.04. So notice it's in a negative direction. Again, it makes sense that these values would match since this is supposed to be an approximation of this value. I want you to notice how similar those are. They are very close to each other. So this is definitely a good approximation. This is the approximate change in y. The next two is just asking you to find what the differential would be. So the definition of the differential is f prime of x times dx. It's asking you what is the equation that you would use for this. So let me create some space. And we will find that. So we first need to take the derivative. So to take the derivative, we really need to rewrite this function. This is going to be x to the 1/2 plus x to the -1/2. So our derivative would be 1/2 x to the -1/2 minus 1/2 x to the -3/2. So I'm going to simplify this just a little bit. We could factor out a 1/2 x to the negative 3/2. And when we do, we're going to end up with x minus 1. Okay, so think about what this is saying. You always want to check by multiplying back through. If we were to multiply back through here, x to the negative 3/2 times x to the first power would be an x to the negative 1/2. And then if we were to multiply back through here, we would end up with this second term. So that's definitely the correct factorization. Now, let's clean that up just a little bit. So this is going to be x minus 1 in the numerator. Then it's going to be a 2 times x to the 3/2. And that's the same thing as 2 times the square root of x cubed. And if we wanted to, we could simplify that just a little bit more as 2x square root of x. So then our differential dy, the definition is f prime of x times dx. So it's just going to be that derivative times dx. So there's our differential. So now we found the differential. We are ready to make approximations if we wanted to. Let's do the same thing for number 28. So our first step is to actually find the derivative for this function. This is going to require a product rule. It's going to require a quotient rule. We also need to think about that secant squared as secant of x quantity squared. So you've got options how you want to do this. I'm going to use quotient and chain. Quotient rule says it's the bottom times the derivative of the top. So I'm subtracting 1 from the exponent, and then I take the derivative of the inside. The derivative of the secant is the secant tangent. So bottom, derivative of the top, minus the top, times the derivative of the bottom, all over the bottom squared. So let's simplify this guy. We have a 2 times an x squared plus 1. And then I'm going to simplify this trig stuff. This is a secant squared x times tangent of x minus 2x secant squared of x all over x squared plus 1 quantity squared. So there's not a lot we can do here. Both of these groups have a 2 and a secant squared in common. That's the only thing I'm going to be able to factor out. That's going to leave us with x squared plus 1 times a tangent of x from the first group and a minus x from the second group. We factored that secant out. And that's over x squared plus 1 quantity squared. So if we wanted to, we could multiply that back through. I'm not going to do that, but we could. So to find the differential is f prime of x times dx. So it's just going to be that fun expression above times dx. So there's our differential.